Hello students, welcome to my lecture series on reinforced concrete structures. In this class, I am going to discuss about a step-by-step design procedure for two-way restraint slabs. This is based on limit state method and we are using codal provisions of IS 456-2000. So let us see what are the outcomes of today's class. After completion of this class, you will be able to know what are the design procedure for two-way restraint slabs. Let us discuss what are the things we have discussed in previous class. In previous class, we have defined what is the restraint slabs and unrestrained slabs. These are the two different types of two-way slabs. So, what do you mean by restraint slab? The restraint slabs are those the slabs whose corners are prevented from lifting up. Those slabs are called restraint slabs. Those the prevention of lifting of a corners of a slabs are made by providing some wall over the slab, or a slab and beams are casted monolithically. And another type of slab is unrestrained slab. This is also called as a corners not held down slabs. So here there is no provision for walls or the slabs and beams are casted monolithically. They are free to lift their corners at the edges of the slab. And we have seen some codal recommendations given by IS 456-2000 for design of this restraint slab. We have seen the codal recommendation. The first codal recommendation is say calculation of bending moments at the central span, that is mx and my, that is of wu alpha x lx square, and my is equal to wy alpha y lx square. Based on these two formula, we can calculate what are the bending moment values are. Then we have divided total slab into edge span, middle span, and another edge span along the x direction, along the y direction. As we are designing the restraint slab, here we have to provide what? A torsional reinforcement. You know, the torsional reinforcement are provided at the discontinuous edges, and when the two discontinuous edges are meeting at a corner, at that particular corner, we have to provide a torsional reinforcement. The intention of torsional reinforcement is to prevent the cracks developed due to torsional stresses at the corners. And when the two discontinuous edges are meeting at the corner, then we have to provide area of reinforcement as a torsional reinforcement, that is 3/4 of ASTX. That is ASTX is area of reinforcement provided at the midspan in x direction. And similarly, we can also provide the torsional reinforcement at the one discontinuous edge and one continuous edge. There we have to provide the area of a torsional reinforcement half of the previous case. What is the previous case? That is when the two discontinuous edges are meeting at corner, we have provided 3/4 of ASTX, and half of that value will be provided when a slab is discontinuous at one edge and continuous at the another edge, that is 3/8 of ASTX. When we have the two edges are continuous for the slab, then there is no need to provide any torsional reinforcement. And also discuss that that mx value will be used for calculation of your area of steel in x direction, and my value is used for calculation of area of steel in y direction, that is the longer span direction. So these are the things we have discussed in previous classes. Right, let us see what is the design steps in today's class. So the first step for designing a two-way slab or two-way restraint slab is calculation of effective depth. Say assume the effective depth of the slab is based on stiffness criteria. You know the stiffness criteria is the L by D ratio. In two-way slabs, Lx by D value may be taken as follows, as per IS 456-2000. So we have a condition given with respect to span and with respect to dead load, with respect to the imposed load or live load acting on that. Say if you want to select or choose the L by D ratio based on the stiffness criteria, when Lx is less than 3.5 meters, that means your shorter span direction is 3.5 meters and live load must be less than 3 kilonewton per meter square, then the Lx by D ratio will be chosen for different grade of steels are like this. If you are designing a two-way simply supported slab and if you are using the steel Fe250 in that, then that Lx by D ratio will be chosen as 35. And if you are using a 415 Fe415 steel for designing of simply supported two-way restrained slab, then we can choose the Lx by D ratio is 28. Otherwise, if you are designing a fixed slab or a continuous slab, then if you are using a Fe250 steel, then that Lx by D ratio will be taken as a 40, and for Fe415 the Lx by D ratio will be taken as a 32. So this is when we have to choose when your Lx is less than 3.5 meters and live load is less than 3 kilonewton per meter square. If the values are opposite to this, say if the values your Lx, the shorter span direction is 3.5 meters and the live load is greater than 3 kilonewton per meter, then how to choose the Lx by D ratio? The Lx by D ratio will be chosen as same as we are chosen for the one-way slab. If your values are like this, say Lx is greater than 3.5 meters and the live load is 3 kilonewton per greater than 3 kilonewton per meter square, then the Lx by D ratio chosen as same as for the one-way slab. Have you chosen for that? So have you chosen for Lx by D ratio for one-way slab is, if you design it as simply supported slab, then Lx by D ratio will be the 25 to 30. Like that, Lx by D ratio you can choose 25 or Lx by D ratio you can choose 30 or in between these two values, say 26, 27, 28 like that. So like that we can choose as same as your one-way slab, as though we are designing a two-way slab, but if it is fulfilling this criteria, the given data is fulfilling this criteria, that is Lx is greater than 3.5 meters and live load is greater than 3 kilonewton per meter square, then we choose Lx by D ratio based on the how we chosen for the one-way slab. Same way we have to choose for this two-way slab also. So this is how we calculate effective depth for the two-way slab. Then calculation of effective span. The effective span of a simply supported slab will be taken least of these two values, right? So we have here in a two-way slab Lx direction and Ly direction, that is in longer span direction also we are providing main reinforcement and shorter span direction also we are providing a main reinforcement. So we have to calculate effective length in both the cases, that is Lx effective in x direction, Ly effective in y direction. The how to calculate that, here we have a two criteria. The minimum of these two criteria will be taken as a effective span for Lx and Lx direction and Ly direction. So what is the first criteria? That is clear span plus effective depth. So clear span means it is a inner face distance to the inner face distance of a support plus effective depth of the slab, that will consider as a one effective length. Another criteria is center to center distance between the support. It is another criteria. The minimum value of these two will consider as a effective length. It may be calculate effective length in Lx direction, that is a shorter direction, or longer direction also. The effective length in shorter direction will designated with a Lx and the effective length in longer direction will be designated with a Ly. The formula for calculating these two is same, that is criteria 1 clear span plus effective depth and criteria 2 center to center distance between the two supports. The minimum of these two value will be taken as a effective span as in x direction or y direction. So this is how we calculate effective span for the slab. Then we have to calculate a load. So for calculating load, we have to choose or we have to consider 1 meter width of the slab. So for that we have to calculate dead load, live load, if any floor finishes those also we have to calculate, and if we add all together, finally we get what is the total load is. So by considering 1 meter width of the slab, the dead load or self weight DL can be calculated overall depth multiplied by width of the slab, or that is 1 meter width of the slab and unit length of the slab multiplied by unit weight of the RCC, that is 25 kilonewton per meter cube. After calculating that we will get a total dead load in terms of kilonewton per meter, and a live load or imposed load will given to you in the problem, and floor finishes also will give you in the problem. And if we add all this, the total load W equal to dead load plus live load plus floor finishes, then we will get total load. And we have to calculate a factored load. We have to enhance the total load by providing some multiplying with some factor of safety. That factor of safety will be taken as 1.5 for limit set of design in collapse condition. So the factor load W equal to 1.5 is a partial factor of safety, and total load is addition of or the sum of all these forces. Then we'll get what is the factor load is. After obtaining the factor load, we have to calculate what is the bending moment, or we can say ultimate bending moment, or I can say factored bending moment. So here, as we are designing the factor two-way slab, the factored bending moment have to be calculated in both the direction. So this is mx is the factored bending moment in x direction, and my is a factored bending moment in y direction. Here there is a formula given for calculation of mx and my as per IS 456-2000 provisions. So mx can be calculated alpha x vu lx square, and my can be calculated my is equal to alpha y w lx square. You know, here alpha x and alpha y are the bending moment coefficient that can be calculated by using a table called 26 IS 456-2000 table number 26. We can calculate. That will depends upon the panel condition or edge condition. Generally we have 9 panel conditions or 9 edge condition of a slab. Among that, according to the what type of slab we have to design for different edge conditions. From there we have to take what are the alpha x and alpha y values. And we know that we have already W calculated in previous case, that factored load, and Lx is effective length in x direction, that also we have calculated in our previous steps. So by using those values, we have to calculate mx and my, and you know that already we have discussed that mx is design moment along the shorter direction, my is the design moment along the longer direction, and alpha x, alpha y are the bending moment coefficients, and w is the total design load on the slab, and Lx is a effective span along the shorter direction. Right. Next, after knowing all those values, we have to calculate the minimum effective depth required. The question is here we have a 2 bending moments, but which bending moment we have to take for calculating the minimum effective depth? Here, among these two, we have to take the maximum bending moment value have to take for calculating minimum effective depth required for a slab. That maximum bending moment value must be equal to that limiting moment of resistance of a slab. So here I am writing mu equal to mu limit. Mu may be a maximum bending moment among the two, that is mx and my. So if it is among these two, mx is maximum, in place of mu you have to substitute mx value. If my is maximum, then you have to substitute in place of mu my value. So here I am leaving as a mu, it may be mx or my. After that, after calculating that, we know that whether mx are maximum or my are maximum. So there we have to substitute here, and mu equal to mu limit, and you know mu limit, limiting moment of resistance is equal to k into fck bd square, and if you rearrange the terms, the d will be under root of mu by k into fck into b. You know that this k value depends upon the grade of steel. So this k value for Fe250 steel, it is 0.148, and Fe415 it is 0.138, and Fe500 it is 0.133. This is the minimum depth required, minimum effective depth required for the slab for the given loading condition. So we have to check this minimum effective depth with the assumed depth what we have calculated in our first step. So if the depth, minimum depth required is less than or equal to effective depth assumed, then it is okay. Right. If not, so if the minimum depth required is greater than the assumed depth, then again we have to revise the depth, and then we have to follow the above procedure for calculating again. So that means we have to assume this depth again, and we will follow the same procedure. Again we have to check whether this d required is less than or greater than or equal to assumed depth. From that again it has to satisfy, finally it has to satisfy this condition. Then until then we have to modify our depths. So finally, if the effective depth, minimum effective depth required is less than or equal to effective depth assumed, then we can say our slab is safe in effective depth. Right? This is how we calculate minimum effective depth by using ultimate moment, bending moment and limiting moment of resistance. Again I am telling you that mu is the maximum value among mx, that is a maximum bending moment or factored bending moment along the x direction, and mu, that is the maximum bending moment or factored bending moment along the y direction. The maximum of those two values may be substituted here in place of mu. Clear? So with this we'll move over to next step. Next step will be calculation of area of steel in midspan. So as I already told you that the total slab will be divided into three portions, that is edge slabs or edge part, that is we have two edge parts for a slab in x direction, and we have a middle portion, middle span in x direction. Similarly you can divide it into the along y direction also. For y direction also we have two edge parts and one middle part. So for first we have to calculate what is the area of steel required in midspan. So that will be calculated with respect to their maximum bending moment values or the maximum factored bending moment values. So if you want to calculate area of steel in x direction, then we have to use here the moment of resistance or maximum bending moment value mux. What do you mean by mux? It is a maximum bending moment value in shorter direction, that is x direction, is equal to 0.87 Fy ASTx into d whole into 1 minus Fy ASTx by FCK BD. In this formula we know what is Fy is, grade of steel is given to you, and we can calculate what is the effective depth, already we have calculated, and Fy is given, FCK is given, and B value is that is a 1 meter. We are designing this slab for 1 meter width, and by knowing all those values we have to calculate what is the ASTx is. And if you want to calculate the area of midspan steel, area of steel in the midspan along the y direction, then we have to use the bending moment formula like this. The MUY is the factored bending moment along the y direction that we have already calculated in the previous step, that equal to 0.87 Fy ASTy d dash into 1 minus Fy ASTy by FCK BD. What is the d dash here? This d dash is effective depth of the slab along the y direction. So dear students, there is a difference between the effective depth of slab in x direction and effective depth of slab in y direction. So this d dash can be calculated by using formula d minus phi. So d dash equal to d minus phi. D equal to the effective depth in x direction. Phi means diameter of bar we are using along the x direction and y direction. Like that we can calculate what is the d dash value is. And here also we can calculate what is the area of steel provided in midspan along the y direction, ASTy is. From both the equations we will get a quadratic equation. If we solve the quadratic equation, we will get what is the ASTx corresponding to this formula and what is the ASTy corresponding to this formula. Then we have to calculate, these are the terms already we have discussed, that MUX is factored bending moment in x direction, MUY is factored bending moment in y direction, Fy equal to yield strength of steel, Fc equal to characteristic compressive strength of a concrete, ASTx is area of steel required in x direction, ASTy is area of steel required in y direction, d is effective depth in x direction, d dash is effective depth in y direction, and this width is b is width of the slab. Generally will take how much? That is a 1 meter width of the slab, that equal to 1000 mm. Right, as I already mentioned you that how to calculate the effective depth here. The effective depth along the x direction will be overall depth minus clear cover minus phi by 2. The phi is the diameter of bar, that will like that you can calculate, and d dash can be calculated d minus clear cover minus phi. This is also phi by 2 minus phi by 2, altogether will get a phi. So we can calculate this d minus phi will be the d dash value, right? Otherwise finally d dash anyhow we can calculate like this, and d value we can calculate like this, and d dash will be calculated a simple formula, that is this d minus diameter of bar. This effective depth in x direction minus diameter of bar will be the d dash for this effective depth in y direction. Simply we can calculate, right? And reinforcement is provided as follows. The steel bars along the shorter span are provided in the bottom layer, and steel bars along the longer spans are provided along the steel bars along the longer span provided above the shorter bar. That means along the x direction we have to provide main bars below at the as a bottom layers. Along the y direction we will provide our main reinforcement above the shorter direction reinforcement. So that it will resist maximum bending moment, right? So the spacing for this main steel will be like this, that is 3D or 300 mm, whichever less we have to provide, as similar case of your other beams also. Next, area of steel at the edge strip. We have already discussed that the total area of slab will be divided into edge strip area and midspan area, and we have the area of steel we have calculated already for midspan. Now we have to calculate area of steel for edge strip. Means here the area of steel provided for edge strip will be minimum area of reinforcement. That is, as per codal provision, the minimum area of reinforcement provided for slab is 0.12% of gross cross sectional area if you are using a HYSD bar, and if you are using Fe250 or the mild steel, that is 0.15% of gross cross sectional area. So this area, this minimum area will be provided as a area for the edge strip of a slab, and spacing will be same, that is 5D or 450 mm, whichever is the less, that will be provided as a spacing for the area of steel at the edge strip. So these are related to your design. So we have calculated B is 1000 meter. We are designing the slab for 1000 mm width, and effective depth you have calculated, and we have now calculated area of steel in midspan as well as a edge strip. This is all about a design part of a slab. Whether this design is safe against the deflection or development length or shear, those things we have to check now. So let me check first whether the designed slab is safe against the deflection or not. So for this we have to calculate what is the percentage of steel that is corresponding to the maximum midspan moment. So that is, if it is MUX is maximum, then we can use for MUX for the calculation a percentage of steel. If MUY is maximum, then we can use for calculating percentage of steel that. So anyhow, a PT equal to 100 AST by BD, this AST may be corresponding to the maximum bending moment or maximum midspan moment. If the maximum midspan moment is it is maximum in x direction, then we have to use here ASTX, that is area corresponding to the midspan direction as in x direction, that will be provided here. So 100 ASTX by BD will be used here. This is corresponding to the what? A maximum bending or the maximum midspan moment along the x direction. If the x directional moment is maximum, then PT percentage will be calculated like this. If the y directional midspan moment is maximum, then PT is equal to 100 ASTY provided by BD, like that we can calculate. So for this I am assuming that ASTX provided here. According to that I will calculate what is the percentage P, percentage of steel, and Fy is a stress in steel under the service load, that is Fs equal to 0.58 Fy AST required by AST provided. So by using these two values we have to calculate what is the modification factor is. So after knowing the modification factor, we have to calculate what will be the L by D maximum, or what is L by D permissible value of L by D ratio. So L by D maximum can be calculated by using basic value multiplied by KT. So basic value will be, as we know that for simply supported slab is 20, and for it is a cantilever slab it is 7, like that, and use that value and calculate the L by D maximum, then compare this L by D maximum with the L by D provided. So if the L by D maximum is greater than L by D provided, hence our slab is safe against the deflection. Like this we can calculate, like this we can check against the deflection for a two-way slab. Then we have to see a torsional reinforcement. As we are designing a two-way restrained slab, so at the edge corners are not lifting off, so there we have to provide a torsional reinforcement. So what is the codal provision for that, and how we have to provide a torsional reinforcement? See, the torsional steel is provided as follows. at corners where slab is discontinuous over the both the edges. Say this is the slab and is the continuous in this direction, continuous in this direction. If you see here, this edge and this edge of the slab is discontinuous. There we have to provide the area of steel 3 by 4th of ASTX. What is that? 3 by 4th of ASTX. You know the ASTX is area of steel provided in midspan along the X direction. That will be provided in 4 layers. Each layer of steel, each layer area of steel will be provided 3/4 of ASTX. Clear? That is this case. So this is a discontinuous edge and this is another discontinuous edge. Here we have to provide area of steel 3/4 of AST. In each layer we have to provide this much area of steel, and that length of the length of the steel reinforcement, torsional reinforcement will be Lx by 5. Lx, you know that length of the shorter direction. Ly is effective length of the Lx is effective length of shorter direction by 5, and in this direction also we have to provide Lx by 5. Right. And next condition we have here, see, at corners where slab is discontinuous over the only one edge. So for this, see, the slab is discontinued here and continuing in this direction. That means this edge of the slab is discontinued and this edge of the slab is continuous. Finally, I can say one edge of the slab is discontinuous and another edge is continuous. Then the area of torsional reinforcement provided is half of this case, that is 3 by 4th of AST whole by 2. That will give me the 3 by 8th of ASTX, and this will be provided in only 2 layers. In each layer of a steel we have to provide area of steel as 3 by 8th of AST. And here also this is same, whatever the thing we have provided here we have to provide is this particular case, because here this is a discontinuous edge and this is a continuous edge, right? And next, no torsional reinforcement is provided where the slab is continuous over both the edges. If you see here in this figure, this end and this edge are the continuous edges, so there is no torsional reinforcement in this particular case. Clear? So this is how we provide torsional reinforcement in the restrained slabs. Then we'll see check for shear. We have to design our slab safe against the shear also. Generally, when we are designing simply supported slab, they are safe against the shear and development length also. Anyhow, we have to check whether how we check the shear, our slab is safe against the shear. So here the maximum shear force edge of the two-way slab is given by Vux equal to W into R power 4 by 1 plus R power 4 whole multiplied by Lx by 2. It is for simply supported slab. Here R is Ly by Lx ratio. If you substitute the W value, already we have calculated R value from this ratio, and Lx is effective length along the shorter direction, then we'll get what is that shear force along the X direction. After knowing that, we have to calculate what is the nominal shear stress is. The nominal shear stress can be calculated as per codal provision of IS 456-2000. The tau V is equal to Vu by Bd. Vu is the factored shear force that we already calculated. B is the 1 meter width of the slab, and D is the effective depth of the slab here. Then we have to calculate design shear strength tau C. This tau C value must be compared with the tau V value. If the tau V is less than or equal to K times tau C, then we can call our slab is safe against the shear. But for that, how we calculate this tau C value is? You know, this tau C values depends upon grade of concrete and percentage of steel provided. Based on the percentage of steel and grade of concrete, we can calculate what the tau C is. Suppose the grade of steel provided, percentage of steel provided is 0.25 and grade of concrete provided is M20, the corresponding tau C value will be the 0.36 Newton for mm square. Like that we can calculate tau C value. After obtaining the tau C value, we have to calculate K into tau C. So this is K is a factor used for calculating a design shear strength value for flat slab. So K value depends upon the overall depth of the slab. If the overall depth of the slab is 150 or less, that will be 1.3, and more than that the values are like this. It is 175, 1.25, 200 mm, 1.2, like this. This is given in the AS 456 2000 in class number 40.2.1.1. So after knowing the K value and after knowing the tau c value, we have to calculate what is the design shear strength for a flat slab, that is K times tau c. And this obtained value of design shear strength must be greater than nominal shear stress. Then we can say that our slab is safe against the shear stress, shear forces. They can resist the shear stresses which are likely to come on the slab. Then we have to check for development length. So development length will be calculated based on the LD, that is 0.87 Fi 5 by 4 into tau bd. Based on this formula, we have to calculate LD. This LD must be less than or equal to M1 by V plus L0. Here M1 is bending moment at the section under consideration. V is the shear force at the section. L0 is the anchorage length. The value obtained must be greater than the value of LD. Then we can say our slab is safe against the development length also. Right? Here I have given one point here. In case of slabs, when the uniformly distributed load is acting, check for shear and development length are mostly satisfied. Then we can omit these steps also while designing the slab. Anyhow, we have to see how to check the slab is safe against the development length and shear. So here I have one design problem, a small problem. Only design. I am not going for checking of anything here. I am designing what is the B, what is the D, and what is the ASTX, ASTY, and what is the area has to be provided in edge strip, like that. So problem is like this. The design a RCC slab for a room of clear dimension 4 meter by 5 meters. The slab is supported on a walls of weight 300 mm. The slab carrying a live load of 40 kN for meter square and floor finish is 1 kN for meter square. Use M20 grade concrete and Fe 415 steel. Corners of the slab are held down. This is most important condition. Whether we have to design a restrained slab or unrestrained slab, that is depend upon the condition of the corner. Here the corners are held down means we have to design it as a restrained slab. So first of all, we have to check whether the given slab is one-way slab or the two-way slab. Anyhow, here we have to design the slab. We are designing the slab restrained means it is definitely two-way slab. But anyhow, we will check here. That will depends upon the longer span and shorter span direction. The longer span is 5 meters and the shorter span is 4 meters. If Ly by Lx equal to 5 by 4, it is 1.25. The ratio is less than 2. So this slab will be designed as a two-way slab, and finally this slab will be designed two-way restrained slab. The given data is like this. Clear span along the x direction is 4 meter and clear span along the y direction is 5 meter. Wall thickness given is 300 mm and live load equal to 4 kN for meter square and floor finish is equal to 1 kN for meter square. FCK is a characteristic compressive strength of a concrete is 20 Newton for mm square and yield strength of steel is 415 Newton for mm square. Based on this data, we have to design. So we know the steps to be followed. The first step would be assume effective depth. So the effective depth can be assumed based on the condition that the length of the shorter span direction and live load given. If the live load is less than 3.5 meters and less than 3 kN per meter square, then we have to choose our L by D ratio is different for simply supported beam. It is, if we are using Fe2 415 steel, that is 28. But if we check here, our live load is 4 kN per meter and our span is Lx is 4 meters. Say that is satisfying this criteria. If Lx is greater than 3.5 meters and live load is greater than 3 kN per meter, then we have to choose our Lx by D ratio as same as how we chosen for the one-way slab. So how we chosen for one-way slab? Based on the stiffness consideration, L by D ratio will chosen as 25 to 30. For this case, I will choose this L by D ratio is 25. From the D can be calculated span by 25. The span is how much given? That is the Lx direction span 4000 mm. So from this assumed effective depth will be 4000 by 25. That will give 160 mm. Here I am adapting clear cover of 15 mm and using 8 mm diameter bar. Then the total depth will be calculated small d plus, so it is a 15 mm and 5 by 2. So that is small d is 120 and the effective depth, that is effective cover is, so it is 15 mm and so it is effective cover, it is a clear cover, sorry, 15 mm and diameter of bar used is 8, so 5 by 2, 8 by 2 will get 179. So assume that it is a 180 mm is the overall depth of the slab. After calculating overall depth, we have to calculate what is the effective span in x direction and y direction. So for calculating effective depth in x direction, we have to choose the minimum of these two values for the simply supported slab. As we are designing, it is simply supported over the 4 edges. First is a clear span for effective depth. The clear span is 4000 mm. Effective depth will be 160. Altogether we have 4160 mm. And second criteria is center to center distance support. That clear span is 4000 and this 300 will be the center to center, that is the width of one support, but center of one support will be give half of the width of the support, another half of the width of the support will be the one full width. That's why I am substituting the 300 mm as a width of the support. That will give me 4300 mm. If you see these two values, the minimum value will be 4160 mm. That will be adopted as a effective span along the x direction. That would be 4160 mm. So this is mm. Then we have to calculate effective span in y direction. We'll use the same formula, that is clear span plus effective depth of the slab. Clear span in y direction is 5000 mm and it is 160 mm is effective depth. Then we'll get 5160 mm. The center to center distance support is 5000 plus 300, that will be 5300 mm, and the effective span in y direction will be Ly equal to 5160 mm. Right, now we have to calculate total load. The total load you know how to calculate, that is sum of the dead load and live load and finishes. Here the dead load will be overall depth multiplied by unit width of the slab multiplied by unit weight of the concrete RCC, that is 0.180 is the effective depth of the overall depth of the slab in meters. 25 is the your unit weight of the concrete. Then the dead load will be 4.5 kilonewton per meter. The live load given is 4 kilonewton per meter. The finishes are 1 kilonewton per meter. The total load will be dead load plus live load for finishes. So 4.5 plus 4 plus 1 equal to 9.5 kilonewton per meter will be the total load. This load must be multiplied with a 1.5 factor. That is 1.5 into total load will be given with a 14.25 kilonewton per meter square. Since this slab, we are designing a single room slab, it is supported on 4 sides. So it is corners held down. It is corresponding to the class number 9. That is all supports, all edges are discontinuous. So for all edges are discontinuous, we will get the positive moment coefficients only along the x direction and y direction. Those moment coefficients we have discussed in our previous class when we were discussing about codal provision class. There we have discussed. If you want to know that, go back to my class and see there. You will get the how to calculate that moment coefficient for when we have the 4 discontinuous edges for this slab. So this is correspond to case number 9. So for that we have Ly by Lx, and that is again less than 2, so it is a one-way slab. And by using the codal values, and we will get the our value will fall between, that is 1.2 and 1.3. We have Ly by Lx values, alpha x value for corresponding to Ly by Lx. Ly by Lx equal to 1.2 we have the values in code, and Ly by Lx equal to 3 also we have the direct value for this moment coefficient, but we are getting here 1.25 is the Ly by Lx ratio. By using the interpolation technique, we can calculate what is the alpha x is. The alpha x will be 0.075. Alpha is direct value, that is 0.056. We'll get from the table number 26 of IS 456 2000. So based on these moment coefficients, we have to calculate what is that factored moment along the x direction, and is the factored moment along the y direction. So alpha x W Lx square is the factored moment along the x direction. So alpha x value will already we know that 0.075 multiplied by your Wx equal to 14.25 into 14.16 is the effective length along the x direction, then mx will be the 18.5 into 10 power 6 Newton into mm. Similarly, you can calculate what is the my is a alpha y value we know, w value we know, lx value we know. Substitute that, we will get what is the my value is. So my is the factored bending moment along the y direction. So that will be 13.81 into 10 power 6 Newton into mm. After knowing this, we have to check against the minimum effective depth required for a slab, that is mu, that must be calculating by using maximum bending moment value with the limiting moment of resistance. So that can be calculated by using this formula, d equal to under root of mu by k into fckb. Here mu value, already told you that this value is taken as maximum bending moment value among the x direction and y direction. If you see this, the maximum value for bending moment will getting in the x direction. So mu value will be 18.5 into 10 power 6. That value we have to substitute in this formula. We will get, if we substitute here, that the d minimum depth required is 82 mm, but assumed is 160 mm. So our assumed value is more than that minimum effective depth required, so hence we are safe in the effective depth consideration. So hereafter we have to adapt effective depth of the slab will be 160 mm, right? So now we have to calculate area of main reinforcement, that is the mid-span region. So along the shorter span, the width of the strip will be, we have to consider 3 by 4th of Ly, and 3 by 4th of Ly is 5.16, that is 3.9 meters. And as already told you that area of midspan can be calculated corresponding to the moment of resistance formula along the x direction, that is mux equal to 0.87 fy astx d into 1 minus fy astx by fck minus b. So this is 1 minus is here, 1 minus this one, not 1 minus this value, 1 minus this one. Just make it correct that. You know, mux is this 18.5 into 10 power 6, that is the maximum, that is the x directional moment, and this 0.87, fy is 4 and 5. astx we have to calculate, this astx we have to calculate, and effective depth is 160, and 1 minus 4 and 5 astx by 20 into 1000 into 160, and then we will get a quadratic equation. If you solve this quadratic equation, we will get area of steel along the shorter span, this astx equal to 332.5 mm square. Similarly calculate, and for this we have to calculate what is the spacing to be provided. I am using here 8 mm diameter bar, and spacing for this bar is calculated like this. The small AST by capital ASTx into 1000. Small AST is the area of 1 8 meter diabar, and that will be 50.3 mm square, and from that I can calculate what is the spacing, s equal to 50.3 by 332 whole multiplied by 1000, that equal to 151 mm. And spacing will be like this, it should satisfy this codal provision. The condition 1 is 38, condition 2 is 3D, condition 1 is 3D, and condition 2 is 300 mm. The minimum of these two value will be provided, but obtained value is less than the codal recommendation, so lesser value will be provided for the spacing. So hence provide 8 mm bars at a 150 mm center to center distance. So next calculate similarly the area of steel along the longer direction, that will be width of the middle strip is 3 by 4th of Lx. With this in this width we have to provide this main reinforcement. So I already told you that effective depth for this longer direction is nothing but small d minus 5. Small d is 160 and d is the 8 mm bar we are used. So 152 is the effective depth, that is the d dash. So the 13.81 to 10 power 6 is MUY, 0.87 FY, for FY is a 4 and 5, ASTY, this one is ASTY, and here D dash is a 152, it is not a 160, please make it correct, 152, and 1 minus 4 and 5 ASTY, 20 into 1000 into 152. If you solve this equation, we will get quadratic equation like this, and by solving this quadratic equation, we will get AST equal to 261 mm square. So this is the area of steel provided along the longer span at the mid span region of the slab, and we have to calculate spacing as similar to as you were calculated in your along the shorter direction. So S equal to AST by capital AST Y. This is a capital AST Y. Please make it correct. into 1000. Small a is the area of one diameter 8 mm diameter bar, that is 50.3 mm square, and spacing would be 50 by 3 whole by 261 is the area of steel provided in the shorter direction at the midspan, longer direction at the midspan, multiplied by 1000, then that will the area, that spacing will be 192, and this value you have to conform with our codal provisions. Here 3D and 300 mm, 3D will be 459 mm, and 300 this 300 mm is compare this, here the 300 mm is less, but the obtained value is very lesser than these two conditions, so provide this 192 mm, hence provide 8 mm diameter bars at a spacing of, this is 190, make it correct again. I copied there from here, I didn't forget to edit this. So 192 mm center to center. Then we have to calculate area in the region of edge strip. The code says the area of steel provided in the edge strip is, there is a minimum area. In this problem we are providing Fe415 steel, that is 0.12% of BD. So 0.12 by percent means 100 multiplied by overall depth, that is 1000 multiplied by overall depth is 180, then we will get 216 mm square. The spacing, I am using 8 mm diameter bar, spacing would be like this. For 8 mm diameter of area is 50.3, and the spacing can be calculated small AST by capital AST in midspan region. I can say it is edge, I have to write the edge here, it is not ASTX. The area 216 I have to provide it by 1000, S equal to 50.3 by 216 into 1000 will get the 232. This is the area we have to provide in edge strip along all directions, right? And the spacing would be conforming to this, that is 5D and 450, and 5D is 900 mm, 450 is that is another is 450, that the minimum value obtained is 232 mm. So provide area of steel is 230 mm at center to center, as diameter of bar used is 8 mm. So this is all for today's lecture. Thank you.